Looks like we have good number of audience. So I made a presentation from this project last month, and today I'm making another presentation which is less than a month. So there will be some slide which will be repeated, so I apologize for those. So this is the research group, and I'll just skip. Thank you very much all the TAP members who are suggesting us time to time. Thanks a lot to Tom who advises us and provides data. Thanks to all the colleagues in Minnesota DOT who provide us the data. All right, so this research project has three distinct objectives. So the first one is when we use structural fibers in concrete overlays or thin concrete pavements, if the fibers contributes in reducing fatigue crack, and if so, can we quantify? The next one is to quantify the contribution of fibers in reducing joint faulting. The third one is if we can increase the slab size when we use fiber. So that is the third objective. All right, so with those objectives in mind, in 2017 8 different cells were constructed. 2 were in the low volume road, cell 139, 239, and another 6 cells were constructed in the main line. Out of these 6 cells, 506 did not have any fiber. Other cells have fibers and were constructed with different design features. We will see in the next slide. So from 506 through 806, we mainly buried the fiber doses. 506 was plain concrete, then 606 was with fibers, the lowest doses, that was with 5 pound per cubic yard. Then this was 8 pound per cubic yard, which gave 30% residual strength ratio. And the next one had the highest amount, which was around 11.7 pound fibers. Cell 139, 239 were ultra thin pavement, 3-inch and 4-inch, and all those cells were having slabs with 6 feet by 6 feet dimensions. Cell 705 and 805 were concrete overlays, unbonded overlays. 805 had wider slab. You can see 12 to 14 feet wider slabs. 805 had narrower slabs, 6 to 8 feet. But 705 and 805, both the cells have similar the slabs with the same length, 12 feet. All right, in terms of the cross section, cell 139, 239 were constructed on 6-inch class 6 aggregate base, kind of weak, I would say. On the main line, cell 705 and 805 were constructed on top of existing concrete. A geosynthetic, uneven geosynthetic layer was used as a separator. And 506 through 806 was constructed on solid, a very thick base, 11-inch of class 5. All right, so quickly we'll see like what kind of distress we have observed. So in order to capture the distresses, distress survey was conducted at different times. The last one was conducted in October and December of 2019. When the esols in the low volume road are around 100 to 100, let's say 20,000 esols, and on the main line around 2.5 million esols. So 2.5 million esols, I would say it's quite more than the esols that we will see in rural road. So just in brief, like cell 139 performed differently. It had shown this kind of crack. You can see on the left side the picture, and then this is just a screenshot of the distress survey sheet. You can see like slab just like broken apart, and some slabs are replaced. Now this is the summary of the cracks in other cells, but 139 we did not incorporate in this comparison because it performed really differently. So cell 239, which was 4-inch thick on relatively weak base, also shown a crack, and 705 and 805 also shown crack. Now 705, which had larger slabs or wider slab, has developed more longitudinal cracks, and the cell which had a narrower slab shown more transverse crack. But overall, the slab with a wider slab resulted in more number of cracked slab. Okay. On the other side, like where we buried the fiber, 506 through 806 did not show a lot of cracks. Only 506 has shown some cracks. I think it was only 3 numbers of crack in the last year. All right. Now, when we compare the percent slab cracked with respect to the esols, and then we try to find out like what is that esols when we saw 20% slab cracked. So in 239, we saw around like the slab cracked, 20% of the slab cracked at 100,000 esols. For the concrete overlays, it's kind of around 500,000. Even though it's still performing, but the current percentage is way more. Like you can see 705 is having more than 50% slab cracked, and 805 is around 30%. Now the others, 506 through 806, are performing really well. All right, so now in order to capture a little bit more what is happening, we also compared the crack length. From the district survey sheet, we calculate the crack length in each cells, and we did it for different times of the survey. Like there are like 4 different surveys. So you can see here what is happening. Even though in the last slide we have seen that around 500,000 esols, around 500,000 or esols, like 20% slab cracked in those 2 cells, but 705 actually failed earlier, right? Now when you looked at the crack length, because those slab dimensions are not same, so when you saw the crack length, now we saw it around 1 million esols, these 2 cells kind of having the similar length of crack. Now when we did little bit of further analysis, in this one we correlated the crack index with respect to the esols. Now how did we find out the crack index? So what we did is length of the crack divided by the total area of the slab. So we have done these analyses, and then we saw that even though the slab, so the cell with wider slab resulted more cracked slab, but the crack index, okay, so the crack index or the length of the crack with respect to the area. So we can say, like, similar amount of the crack, similar nature of the crack, we can see up to 1.25 million esols. So if we say the rural road has around 1 million esols, so in terms of the crack index, the wider slab and the narrower slab still can perform the same at 1.25 esol, and after that the larger slab failed in a aggressive trend. In terms of joint faulting for cell 139, 239, The faultings were not bad. 705, 805, the same within 1 to 2 millimeters. For 506 to 806 on the main line, we have seen more faulting on the plain concrete, which is like 506. You can see it didn't have any fiber, 0 pound per cubic yard, so faulting kept on increasing. But which has fibers with the fiber doses, you can see the faulting was low. 806 had the lowest one. Cell 606, which was inadvertently constructed with 6-inch slab compared to others 5-inch slab, have shown kind of similar faulting with cell 706. So these are these results shows the faulting versus ESOLs. Now you can see the red one at the top. This is 506, and the two intermediate graphs are 606, 706. So 606 had 6-inch thickness, so that's why the faulting is a little less. And the 706 were 5-inch but had more fibers. But these two curve actually gives a good kind of indication that maybe like 1 inch of extra concrete is equal to 3 pound per cubic yard of fiber. That's the fiber that we used. I mean, like, that's the extra fiber we used in cell 706. So with the faulting data, we have created faulting models with respect to ESOL, slab thickness, residual strength, modulus of subgrade reactions, and then so far the model looks like this. So again, what we are seeing is here 606 and 706, the faulting value were pretty close. As I mentioned, the 606 was 6-inch, 706 was 5-inch. 706 had 3 pound more fibers, but faulting wise they perform kind of equal. So that's what I am just saying, that maybe 1 inch of extra concrete and 3 pound per cubic yard of fibers are probably kind of equivalent with respect to the faulting, but this is just based on very limited data. So here you can see kind of the steps in the correlations. So this kind of correlations arrive because when we measure this faulting in the spring, it is more, and in the fall or in the summer it is less. So this is the reason this kind of shape has occurred. And this K, what is modulus of subgrade reaction, that actually have characterized this kind of trend. When we remove this K, the faulting curves become like this. We are still working on these faulting models. We plan on validating these models with respect to the field data that we will be getting for this spring. So we will not use those data in the model, but we will plot them to see the accuracy of our models. Sensor data, we actually analyze temperature, relative humidity, crack width, environmental load and strains, following what deflectometer data until the second year. I'm not including these things in this presentation. So we also did some laboratory study where we studied the creep of the fiber. What we have done, we crack the beam and then hold in tension for 10 days to induce some creep. This just slide shows what we have done. You see, if you just keep the beam in tension and then slowly fiber gives up, maybe the fiber is pulling out of the concrete or it gets some plastic elongation. So we could see some creep occurs, and we believe that the same thing can happen in the field, but this can be changing using different types of fibers. We do not know the fibers that we have in the market right now, whether these are good for the pavement. That's a question, because those were not actually designed for the pavement. Those were actually designed for the industry slab, which definitely experience different kind of load than what fibers get in the pavement. So we might need to think about this. We creeped some fibers and we did not creep, and then we also conducted some joint performance test, and you see when we creep the fiber, the load transfer efficiency was less. So definitely the creep affects. Now future work, so in terms of the analysis work and then whatever the data we have, we really did a good progress. As you saw, like we already developed faulting models, but we still have to develop a fatigue crack model for FRC thin pavements and overlays. Fiber contributions in terms of, let's say, residual strength may not be a variable due to the lack of data, although this was our main goal, to find out the influence of fibers in the fatigue crack. But since cell 506 through 826, where we varied the fiber, we didn't see a great variation in the crack. Only one cell cracked that didn't have fiber, right? So, but we will try to develop some kind of curve for different cells, at least for different thickness. We can get those curves. So the model will be function of, let's say, ESOLs, the base thickness, the overlay thickness, or the pavement thickness. With respect to that, we are still, our model is kind of ready, but we are still working on it, refining it. The accuracy of the model is also good. We want to validate with the 2020 data now. So as soon as we'll have the data, we can check the accuracy. Now we also had an objective that we will investigate if the fibers can help in increasing the size of the slab. We have seen, if we compare the percentage of the cracked slab, then a narrower slab perform better. But if we really go with the crack index, or we see the crack length with respect to the total area of the cells, then that's a good news. We probably can increase the slab size, or we can increase the width of the slab size rather. Also, we will compare the crack index with respect to IRI, which we have not done yet. We will be doing it in next few weeks. Means like if we have more crack length versus less crack length, how it influences the IRI, and then we can actually make a comment if we can actually increase the slab size without decreasing the IRI or without changing the IRI. So we are also doing an FEM investigations to find out the effective slab size. So this will be in addition to what we are getting from the field. So we are working on that too. We are behind the schedule on submitting the task report. I was just talking to Ben, probably we committed a lot of reports, which we probably could put a lot of that this analytical works in probably less number of reports, but we are working on those reports now. So these are the tasks that I mentioned. So this will be within the current project timeline, but I think our research doesn't stop here. So after that, actually next thing what we should do is generalize structural model, right? When we say structural model, that will be like finding out the stress or strains for the given design feature. That includes fiber contribution. So, and that need finite element modeling of the main road sections using sensor data, and then a generalized performance model like a fatigue model or faulting model. The model that we are proposing right now, those are good, but those are like we did not consider a great variation in the base properties or modulus of subgrade reaction. We confined ourselves with the main road. So in order to create a generalized model, we need some more data, more probably test cells, in order to make a kind of generalized model, let's say the model that we develop, which can be used for different states. So more test cells maybe in the next phase with varied design, and also we did not use different fibers. Maybe in the next time we should construct some cells with different types of fibers, which is important. And in the meantime, if we get some pavement specific fiber or something which will not pull out of the concrete or pull out less and will be laterally stiffer, or it will not have more plastic elongation, those kind of fiber. Also, we need to incorporate the creep effect. As you saw, the creep affects the joint performance. So these are the things probably we need to be looking at. And then if we look at, actually, we probably can incorporate the fibers effect into the design procedure. Right now, let's say we have BCOA, or the other one came from unbonded concrete overlay. So in all those things, we do not have a mechanistic way to incorporate the contribution of the fiber. I think the next step should be focused on that. So just like a couple of slides what we're doing in the finite element modeling, so we already developed models. So this slide shows the model that we created for cell 139 and 239. We consider 4 feet wide shoulders, just like the way it is there. And then we have like 6 slab model. We are using the same amount of the track load, or the same wheel configurations, equivalent configurations what we have. We also created models for 506 through 806 so far, but we are still working on refining a lot of stuff. We did not start running like a batch of the files yet. This is just like as an example of different stress. So our models are pretty accurate. You can see like the maximum principal stress on cell 139 was 519, which tell us why it is cracked really early. 239 and 506, you can see this particular trend tell us why we are seeing different cracks. So this finite element work will also answer a lot of questions. Also, it will answer provide some data for the cells that for the designs that we do not have in the main road. So with that, actually, I would like to conclude, but I would not read all those separate conclusions. So rather, I will take questions, I guess, and if there is any question related to the conclusion, I can read those. Otherwise, I am good to take questions. Brett, if you are ready to allow people ask questions.
Does anybody have any questions? Manik? Hopefully the next phase we'll be able to get a few more and get some more data to try to flesh this out a little bit, but it is intriguing. Well, I appreciate taking the time to give the presentation. When we get done, if we have any time left, we can kind of have an overall, if anybody's got any questions, if anybody, but I appreciate it. And with that, Tom, I don't know how we lecture control and get the next presenter up. And thanks.
This has been Worrell. I have one question. Tom, did you start the recording?
Yes.
Okay, I didn't see the red button.
Yeah, it's on.
Okay.
There we go.
And I guess, Manik, if you have ideas for next construction go around, just jot things down in an email.
Sure, okay.
Kind of in a few of our brains, start thinking down that way.
Sure, thank you,
thank
you, Ben.
Thank you.
Yeah, all right, we should continue this one. Thank you. So,
see, next up is Sheue.
Yep. Let me start sharing my screen here.
Yeah, go ahead.
Okay.
I gotta stop mine. There we go. Let me know if I need to do something on my end, but I think.
Okay. It's taking a while to load the file.
Yep, okay.
Okay.
Now,
Tom, you are not seeing my screen, right? Everybody?
Nope.
Not? Okay, thank you. Just making sure so that I do not show something what you should not see.
There we go. We're starting. It says loading now.
Okay. Perfect. Can you see it now?
Yes. Yep.
Okay. Yep. So good afternoon, everyone. I'm Sheue with WSB, and today I'm going to present on the concrete pavement restoration for bonded concrete overlay of asphalt synthesis. So just to give a quick update on this project, this synthesis has been completed and we're now working on publishing the report. CPR techniques have been used widely to repair traditional concrete pavements, but these techniques may be or may not be applicable to BCOA pavements. So over the past decade, the popularity of BCOA pavements have grown in many states, and many of those projects are now reaching an age where a rehab is needed. So the purpose of this project is to compile a synthesis of current practices of repairs being used on BCOA projects by the contributing states. So the few topics covered in the synthesis include the repair techniques from participating states, general performance data, which includes the improvements and extension of service life of the repairs done, the cost related to the type of repair, and the time taken for the existing distresses to reflect through. We have also included the literature review performed on different types of repair. So in this synthesis, BCOA pavements are defined as concrete overlays that are between 3 inches and 7 inches thick and are placed on an asphalt layer with a minimum of 3 inches. A rehab should be considered when the distresses are causing rot issues or the panels have deteriorating cracks. From the literature review performed, the typical load-related distresses observed on BCOA pavements are transverse cracking on larger size panels, longitudinal or diagonal cracks on medium-sized panels, corner breaks on smaller size panels, and also reflective cracking from the underlying asphalt pavements. Joint faulting is also considered one of the main distresses caused by truck traffic and vertical temperature gradients. So in this project, survey questions were sent out to participating states to collect responses on their experience on repairing BCOA pavements. So once we've got the survey responses back, we sent out follow-up survey questions, mainly asking for more details on the repairs done. So there are a few types of repairs that we have seen from the participating states, and the main type of repair is full panel removal and replacement. So for this project here, there was longitudinal cracking in the outer wheel path and or the paved shoulder. So this cracking has been observed in overlays with integral widening. The widenings are generally tied to the mainline overlay, and this cracking was believed to be caused by the heaving underneath with rigid tie bar connecting the overlay to the widening unit. So the differential movement appears to induce a crack in the panels. This cracking is sometimes isolated to individual panels in the outer wheel path, but also sometimes runs continuously through a series of panels and extends into panels that are closer into the center line. So the picture on the left here shows the repairs that's been done. So most of the patches were in the outer 3 feet of the driving lane adjacent to the integral widening. Saw cut was placed at a sufficient depth to ensure that the existing tie bar at the bottom of the PCC overlay would be completely severed. So the picture here shows the repairs that's only being done in recent years, and from what we have heard from the DOT, the traffic levels on this project has been stable since the repairs, and the repairs are believed to be in good condition after 2 years of the repair. So next, another issue that the DOT experienced was construction issues. So the overlay was constructed thinner than designed. So you can see over on the picture on the right here, it showed the thin section. So it was about 3 inches as compared to the original design thicknesses of 4.5 inches. So slab cracking was severe in these thin areas, so the patching was required to improve the condition of the pavement. In this case, additional asphalt had to be removed so that the patch portion of the overlay could be placed at the original design thickness. The patching appears to have improved the pavement condition index, while the ride quality remains stable based on the pavement management data we got 2 years after the repair. Another factor that prompted the full panel removal and replacement was support issues. So premature failure was determined to be support issues where there was too much moisture in the subgrade material. The AC was also observed to have extreme stripping issues in this case. So the repairs performed was full depth removal and replacement. So subgrade correction was conducted by removing several feet of the existing subgrade material, followed by replacing it with aggregate fill material. And geotextile fabric was also installed prior to the placement of the new fill to try to minimize the contamination of fines into the fill material. So the slab itself was quite thick, about 9 inches deep, so it could be a free-floating panel without joints. And bond breaker was used to line the interior. I can see in the picture on the right here. The repairs also included rebar placed at 4 inches from the base. The repair had held quite well with no distress to date, and it was about 19 years since the repair was done. Another issue was lack of consolidation for another project here. So the repairs included removing and replacing the concrete overlay with reinforcing bars installed. The bars were installed to promote transfer of loading, and the joints were established the same. So these repairs were done in 2000, and they have been performing well to date. So it's about 20 years after the repair. Another project that we have seen had longitudinal cracks formed along the inside dowel bars, which then migrated to the mid panel and then continuing longitudinally down the road each way. So 5 years after this project was constructed, the pressure generated from the summer expansion on areas where this dowel bar baskets located was causing the concrete to break loose at the cracks as shown in the picture here. So the repairs were performed by sawing out the bad areas approximately 2 to 3 feet from each side of the transverse joint, and the corners of the removed area would then match the existing longitudinal cracks. So full depth repairs performed on this project also included removing the existing dowel baskets with no replacement, and also sawing the transverse joint to match the O joint. However, these cracks had extended the entire length of the road, so decision was made to cross-stitch and seal the longitudinal cracks, as you can see on the picture on the left. So the pavement has not moved as much in the areas of stitching after repair, and the pavement ratings in 2018 indicated that the road was in good condition. So another type of repair that we have seen is retrofitting dowel bars and diamond grinding. Excuse me. So faulting, excuse me, Faulting at the transverse joints was caused by high truck traffic. And for this project, coring results showed that there was debonding at the interface between concrete overlay and the underlying asphalt. So the repairs consisted of retrofitting dowel bars and diamond grinding to improve the ride quality. So 1-inch diameter dowel bars were used in this case. And in order to hold the dowels in place during backfill, they were fitted with expansion caps and also seated in chairs. For these projects, the repairs were well received by the users. Another type of repair that we have seen is rebars and roofing fabric installed. So for this project, the causes of distress were a combination of fatigue cracking due to inadequate overlay thickness and also the loss of panel bonding with the HMA due to the lack of joint seals. So over on the picture here, you can see rebars were installed into the asphalt to enhance bonding, and a strip of roofing fabric was installed to try to mitigate reflective cracks. The picture here shows the performance of the repairs 2 years after. It seems that the roofing strip is effective in mitigating reflective cracking. However, there was other leading edge distresses observed in the repair. So there's only one specification that we have found that specifically talks about the repairs of BCOA pavements, which is from the Texas DOT. So I won't go through the whole spec here, but just to point out a few procedures that were being mentioned in the specs. So one of them is to mill 1 inch into the underlying asphalt layer, and additional milling needs to be conducted if the asphalt at the interface level to ensure adequate bonding with the asphalt. So if a crack is present in the asphalt layer, a bond breaker such as duct tape should be placed over the cracks and extend 2 inches on each side of the crack. The specs also call for sawing and sealing all the construction joints and saw the contraction joints to a minimum depth of 1/3 of the concrete overlay or to a minimum depth of 1 inch for dry early saw cuts. Next, we'll move on to the summary of the survey and literature review. So there are a few sources that we have found from our literature review, which were from the ACPA, MnDOT, NCHRP, University of Pittsburgh, and the National Concrete Pavement Technology Center. So the most common type of repair is full depth removal and replacement of concrete panels. Since BCOA pavements has such thin overlay that it is more cost effective to perform removal and replacement of panels as compared to other types of rehabilitation methods. This type of repair has also been cross-referenced across different reports that we have found from the literature review. So here we'll talk about a few typical techniques that we have found from the literature review. So one of them is that the removal of distressed panels should be conducted in a way that the milling action does not cause a disruption to the surrounding panels. So in this case, saw cut or milling within 6 inches from the edges of the panel may be beneficial. It is also recommended saw cut or milling of the panels should be conducted at full depth of the concrete overlay. A few sources stated to even extend the milling beyond 1 inch into the underlying asphalt. So light jackhammer can be used to break up the concrete for removal. And extra care should be taken to mitigate reflective cracking, such as placing bond breaker directly on the crack and sawing the new joint over the reflective crack. It is advised that panels should not be replaced with asphalt materials since there will be bonding issues between the asphalt patching and the surrounding concrete panels due to the movement of the concrete panels. fast setting concrete could be used if the traffic opening time is a constraint. So in the event where a misaligned transverse joint is created to try to mitigate reflective cracking, longitudinal joints should be placed on both sides of the misaligned transverse joints to prevent the development of cracks from these misaligned transverse joints into the adjacent panels. No load transfer device such as DALBA should be installed during the repair. However, it may be feasible to retrofit DALBAs for repairs of overlays that are 6 inches thick and greater to try to address faulting issues. Contraction and construction joints should be sawed, and the joints are typically sawed to a depth of 1/3 of the overlay thickness. So another type of repair is cross-stitching the cracks, but this type of repair is very costly. Asphalt patching can be used, but only for temporary repair. Diamond grinding can be used to remove joint faulting. However, if the root cause of faulting is not addressed during grinding, faulting will eventually resurface in the future. If there are more widespread distresses or underlying base or subgrade issues, a more robust rehabilitation method would be required. So if a localized repair is chosen by removing and replacing a portion of the underlying poor material with aggregate fill, geotextile fabric can be used as a separation layer to prevent the contamination of the underlying material. A full depth concrete repair, which can be extended to the layer below asphalt, is a good alternative if all or most of the asphalt has been removed. So in our synthesis, most of the information collected were on the type of repairs and the procedures of conducting a repair. However, there were not much documentation on post-repair monitoring activities of repair performance. So last, I would like to thank all the TAB members and participating states for contributing to this synthesis. So this concludes my presentation for today, and I'll open up the floor for questions.
Thanks, Sheue. Does anybody have any questions? Hey, Tom or Ben, do you know when this, has this thing already been published, the synthesis?
No, we're in the middle of, we just turned it over to be published, so I would imagine maybe a month or less.
Okay. Well, that way, if people have any questions or anything, they'll be available for them to read and get the information in. All right. Well, thanks again, Sheue.
Yep.
And we'll get the controls flipped around and get to, I think it's Hamad. I think if I read the email right, he's going to be filling in for Peter.
Yes, Brett, you're right. Can you hear me better?
I'm working on it. There we go. Oh, maybe she can stop. If Sheue can stop presenting, that'd be helpful. Because I tried to take it over, but it's not. I'm hitting stop here, but it keeps loading. There we go. Okay. Give it a try, Hamad, if you can. Just slow loading as usual.
Everybody's Skyping or Zooming.
Mm-hmm. There we go. We see loading.
Good sign.
I'm not sure if you're going to see my PowerPoint or a busy desktop.
We see one of those tunnels of... yeah. There we go. Yeah,
There we go, Mod.
now we're good.
Great. So do you hear me well?
Yes,
Yeah.
we can.
Yeah.
Great. Awesome. So good afternoon, everybody. This is Sadati from National Concrete Pavement Technology Center. Thanks for the opportunity for being here today. And my presentation is also going to be focused on use of fiber reinforcement in transportation infrastructure. Actually, the project that I'm going to be talking about involves use of fiber reinforced concrete mixtures, FRC mixtures, in 3 construction projects in the state of Minnesota. And these projects include a roundabout and 2 overlays with interesting research ideas involved in all these projects. I'm going to have a brief summary and introduction of the 3 projects, and later on I'm going to mainly focus on the FRC roundabout. But we know that the use of roundabouts can improve and help us with enhanced safety and traffic flow in rural areas. And the idea here with the FRC roundabout project was to see if we can use a structural fiber reinforcement and FRC mixtures to reduce the need for sophisticated joint layouts. As we can see later on in this presentation, in this project, we are discussing construction and performance of a jointless FRC ring in these roundabout projects. This project also involves 2 overlays, construction of 2 overlays, thin overlays over existing asphalt pavements. And there are also some interesting features involved in the design and construction of these overlays as well. We have different features to investigate. Different type of fibers are being used in one of the overlays, different joint spacing, and also a very interesting idea to investigate the use of early age loading for increasing the joint activation in overlays. This is here I have an aerial photo of the roundabout itself. It's located near the city of Sleepy Eye in Minnesota. And here, if you can see my cursor on the right side of the slide, this is the jointless FRC ring that we are going to be talking about today. The 2 other projects, project number 2, Trunk Highway 63 FRC overlay, which was constructed in July 2018. Just as a brief introduction, it's a 5-inch thick FRC overlay over an existing asphalt pavement in a stretch of 12.5 miles. The majority of the project was constructed with joint spacing of 6 by 6 feet. But there was an alternative joint spacing design 6 by 12 to investigate the faulting and long-term performance of this joint spacing as well. There were no dowel bars in the design, and 3 fiber types were used in construction of some areas of this project. It was located on Highway 63 here, southeast part of the state of Minnesota. And the 3rd project is also constructed in August 2018. Again, a 5-inch thick fiber reinforced overlay over existing asphalt, almost 7 miles long, and joint spacing of 6 by 7, 2 traffic lanes, each 12 feet wide. Again, no dowel bars, but both overlay projects were exposed to early age loading, and it was a very interesting idea, after the stall cutting was done, to have a water truck filled with water, different weights, and have it pass over the overlay and see if we can activate the joints with early age loading or not. Because of the time constraints, I'm not going to be able to discuss the details of the 2 overlay projects, and today we are going to be mainly focusing on the FRC roundabout. So the scope of the project that CP Tech Center is involved has 3 tasks. We have started working on these tasks in early July 2019. The first task was to develop a construction report for the FRC roundabout. For this, we needed to go over all the construction documents, review all the photos and interview all the engaged parties, gather all the available test data, and to develop a report that's going to be usable for both the NRRA team members and anybody else that's going to be interested in this type of project. This report is submitted and approved. The second task of the project was to develop a construction report for the 2 FRC overlays. Again, the same thing, go over the documents, review the available test data, review all the photos, and interview all the engaged parties from contractor side, from the DOT side, and anybody else that was engaged in this project, and try to see if there were any unique experiences that could be involved in the report and to be documented. This report is also submitted and it's under review. Actually, I'm working on the revision right now, which is going to be due later this month. But the third task was to have a 3-year monitoring of the performance of the FRC roundabout. So the first year report was submitted and also approved, and this presentation is going to be mainly focused on this part. So as I mentioned, the roundabout was placed close to the city of Sleepy Eye in southern Minnesota at the junction of Torng Highway 4 and Canyon State 8 Highway 29. Here I have the traffic data that was used for the design of the project in here. And some more details about the project. Overall, something about 170 cubic yards of fiber reinforced concrete mixtures was used for placement of the jointless ring itself, and it was placed over a 6-inch thick MnDOT Class 5 aggregate base and a granular sub base. The thickness of the FRC ring was 7 inches and the width of the section was 16 feet. And placement was done by contractor Hoffman Concrete, and concrete supplier was Semestone Products. Here we have a schematic drawing of the roundabout itself. Hopefully it can better show the FRC ring and the project itself. The green areas here is the jointless FRC ring, which is of the main interest in our study. There were no joints, as I mentioned earlier, no dowel bars, of course. For the truck apron here inside, we had joints and there were 1-inch dowel bars involved in the design. And the construction was took place in September 2018. Here, in these yellow areas, in 3 different sides of the roundabout, there was a test pour a few days before the main pour and the main construction of the FRC ring to see the performance of the concrete mixture itself and to see if there is going to be any problems with the workability, because high dosage of fiber was being used in the concrete mixture. And here I have a picture from our site visit. This is the truck apron, colored concrete was used, and we have joints here. We have 1-inch thick dowel bars. But the FRC ring itself, there were no joints here. We have a wide open crack, it's not a joint. And there were no dowel bars, just fiber reinforcement. This is the concrete mixture design that was used for construction of the FRC ring. The cementitious material content was 650 pounds per cubic yard, 20% of which was Class F fly ash. The design water cement ratio was 0.42, and 6 pounds per cubic yard of synthetic fiber was used in this project. The fiber was produced by BSF Master Builders. It was MAC 360 FF with aspect ratio of 83, and actually it was a hybrid of micro and macro fiber to control both the shrinkage, cracking, and also add to the structural capacity of the concrete mixture. So construction took place in September 2018. It started from the west side of the roundabout. 2 crews were working on the construction, trying to advance from both directions, both to accelerate the construction and also to avoid formation of cold joints in concrete, especially known that there were no tall bars included in the design. No problems were reported with the construction, nothing wrong with the workability of concrete, everything worked well. And here I have a picture from the placement. Something interesting, during the test pour and also during the main pour, it was observed that use of hand vibrator can cause some problems with fiber distribution. It can cause fiber nesting. So during the construction, it was decided to go with roller screeds and also hand vibrator, but the use of hand vibrator was just limited to the areas of contact between the two successive loads of concrete to make sure that the two concrete mixtures on two different batches are going to mix properly and there's going to be no cold joint in the concrete. Very good fiber distribution, as we can see from this picture. No problems with that, and nothing reported at all, and no problems with finishing. That was, done right after the placement of concrete. As I mentioned, a cool feature about design and construction of this roundabout was to eliminating joints and dowel bars. But in order to activate cracks, it was decided to go with notches all around the FRC ring. Here I am showing just 2 notches on this schematic drawing, but notches were placed all around the FRC ring. And here on the left side in this picture, we can see 2 saw cut notches. These notches were 15 inches long and 1.5 inches thick, all of them saw cut after the construction and also sieved. Testing the concrete was performed during the construction, taking samples for measuring the fresh properties, plastic air content, slump, and also controlling the water cement ratio based on the concrete batches. There were some problems with one of the delivered loads of concrete, too much air, but rest everything was fine. Average of 8% age in plastic concrete. Slump average was 3.75 inches, and the average water cement ratio based on the batch tickets was 0.4 compared to 0.42 that was specified in the design. Samples also were taken to monitor the hardened property. Cylinders were cast during the construction and tested at 28 days to measure the compressive strength. As you can see, the compressive strength average was 4850 psi at 28 days. Samples were stored in field for 5 days and then transported to lab and moist cure up to the test of age of testing. Well, with the use of fibers in concrete mixtures, it was interesting to see the post-cracking behavior and increase in flexural properties of the mixture as well. So during the construction in field, beam specimens were cast and transported to the University of Minnesota in Duluth later on for testing. We have a summary of the results in here. Average modulus of rupture at 28 days, 590 psi. 130 psi residual strength, which was lower than the specified amount of 175, and residual strength ratio at span 250, 22%. A few days after construction, cores were extracted by Minda to control the concrete thickness. The desired thickness was 7 inches, and the average thickness based on the core data was 6.7 inches, slightly less than the design value. Minda's staff were visiting the project at different time steps after the construction to monitor the crack development and crack propagation in the reinforced ring. And we also had the opportunity to be with them in October 2019 and have a field inspection to see how the concrete is working and what's the status of cracking in concrete itself. Overall, I should say, after more than 1 year of being in service, very good surface texture, no signs of durability problems and material related distress. And I should say the only problem that we could see was the random cracking. Here I have a crack, a map of crack distribution as of October 2019. The green area, the jointless fiber reinforced ring, we had 18 cracks. Some of them were very tight and some of them very wide open. And as you can see all over the ring, we can see the cracks. But unfortunately, we noticed that not all the cracks are initiating from the notch areas. Okay, as you can see from the picture on the left side in this slide, some of the cracks initiated from the notches as it was desired, but some of the cracks, as we can see in the two other pictures, were not really initiating from the notches. Some of them just maybe a few inches from notch, or some of them between two adjacent notches. Thanks to the traffic control and support provided by MinDOT, we were able to gather some more information during the site visit in October 2019. MinDOT's fault meter was used, and also MinDOT's falling rate deflectometer was used to gather more information from the cracks. We also did a comprehensive crack survey to measure the crack width for all of the cracks in these projects. And later on we decided to go with some of the cracks that were wide open and some of them that were relatively tight from different areas of the fiber reinforced ring to do measurements and determine the load transfer efficiency and also determine the extent of faulting. Here I have a lot of data in this table. I'm not going to bore you with them, but here in the fourth column I'm showing the cracks that were initiated from notches. 8 out of 18 cracks were initiated from notches, like 44% of them. And faulting was, we did get varying numbers for faulting, starting from 0 up to values like 5.5, 6 millimeters in faulting, and also different numbers for load transfer efficiency for different cracks. We are going to see them in this slide. So when I was analyzing the LTE data, I could see two different trends depending on the type of crack and the crack width that we were working with. For the tight cracks, as we can see on the left side, for both the approach and the departure traffic, LTE testing done before and after the crack, we were seeing very comparable trends, very comparable performance. Numbers were same, and the deformation patterns were similar too. But for the wide open cracks, as we can see from the graph on the right side of the slide, the deformation patterns were totally different for the departure and the approaching traffic. Means that with the wide open cracks, even though we had fiber reinforcement, the load transfer efficiency was really compromised. So we decided to try and quantify the LTE, load transfer efficiency, as a function of crack width. Here I have a summary. Crack width on the horizontal axis and the average LTE numbers on the vertical axis. As you can see, there is a decreasing trend as we have increase in crack width. LTE numbers are dropping rapidly, and on average, if you focus on this area of the graph, on average, if we are trying to reach an LTE of say 80% or higher, we need to keep the crack width limited to like 0.5 or 0.6 millimeters. It was very interesting observation. Hopefully we can continue monitoring these cracks and this FRC ring in future to see first how the crack width is going to change over time, how many new cracks we're going to have, and how this graph is going to change over time, with more cracks being investigated and a wider range of crack widths being investigated. MIRA test, non-destructive testing using MIRA was also performed during the site inspection to measure the thicknesses. Testing was done at different points, and results overall are in good agreement with the data that was observed from cores, thickness varying from 6 to 7.5 inches at different areas of the jointless FRC ring. So, as a summary, I should say, first, it is a very great experience to be involved in this project. Very nice, idea to go with jointless section, but high dosage of structural fibers, fiber reinforcement to see the overall performance, long-term performance, and cracking behavior. So far, after over 1 year of service, there are no problems with durability of the material. There were no problems with the workability of the material given the 6 pounds per cubic yard of fiber being used. No problems with construction. And the only problem so far seems to be the random cracking in this FRC ring, which means that maybe the considering the notches only might not be the most comprehensive and conclusive method for controlling the cracks in such designs, and this is going to need maybe further study to investigate different scenarios for controlling and crack propagation in such projects. So hopefully the monitoring of the FRC roundabout is going to be continued for 2 more years. During this time, we are going to keep an eye on the crack propagation. We are going to monitor the cracks and see how they're going to change over time, and if there's going to be any sign of distress in material, considering the harsh environmental condition that the concrete is exposed to. And hopefully we will have some more cool data to share with you in future presentations. Having that said, I would like to thank our colleagues at MinDOT and NRRA Rigid team members for supporting us and working with us on this project. And also, I would like to appreciate the support and the technical discussions provided by many individuals from MinDOT and contractors that were involved in these projects that helps us develop the reports and have some good discussions and good data to share with the rest of our team members. With that, I'm going to conclude my presentations, and I'm going to be happy to take any questions.
Anybody have any questions for Hamad?
Yeah, Bernard, type one in, or Bernard, you can unmute yourself, and if you want to directly ask him.
Well, based on this is a fracture mechanics thing. Can you hear me?
Yes, sir.
Yeah, the crack propagation, the notch initiation would definitely be a very good study of fracture mechanics. However, I wanted to ask you, Dr. Sadati.
Yes, sir. Hello?
Oh, must have lost Bernard.
Oh, again. Sorry. Let me take it again.
No, we are hearing.
Bernard, I'm hearing you.
Okay. So the question is, would you subscribe to initiating the notch in the inner circle rather than the outer circle going forward? If you were to do this again, I mean, if we were to do this again, would you subscribe to initiating that notch at the inner circle that's the smaller circle rather than the outer circle?
It can be an interesting idea. Yeah, why not? It can be an option for further study. Some of the cracks, however, I have seen in the roundabout seems that they were initiating from the outer side of the ring. For example, if you can see this slide here, for example, crack R18, it's started from outer side of the ring itself, or crack R3, or crack. But definitely, yes, that's, to my mind, that's going to be a very good option and to consider in further studies. Yes, to have notches from inside as well.
Any other questions?
Yeah, I have one question for Dr. Sadati.
Yes, sir.
This is Manik from UMD. So Now, the objective of the project was like if fiber could help in this kind of jointless roundabout. So, do you have any conclusion on that? Like, if this roundabout did not have any fiber, do you anticipate a different behavior? As we see the load transfer, we probably didn't get any benefit. So, like any other thing that you have thought about?
It's not that easy to make conclusion without having the experimental data. I would say yes, most probably, maybe even wider, crack openings, or maybe more number of cracks. Right now we have a lot of tight cracks, which I would say are being held together with the help of fibers. So if we didn't have fibers, maybe they were more open. I'm not sure if that would be true for all around the ring or not. So far, I would say the main conclusion is that the combination of the fiber reinforcement and the notches that we had in this project are not enough. Okay, as we can see, we do not have uniform crack width all around the circle itself. In some areas, we have very low LTE numbers, means that we have lost the good load transfer efficiency, and we also have some high faulting numbers. Maybe it could be even worse if we didn't have the fibers, but I would say it's a good experience so far to learn how the performance is going to be. Is this the complete design? I would say no, but this is something that will definitely need more investigation, maybe some modeling and some more experimental work. Maybe a combination of fibers and dull bars and joints, maybe, or as Bernard mentioned, maybe to have the notches from inside the ring as well. These are all scenarios that could be investigated.
All right, thank you. I'm just curious. Some of the cracks are like 6 millimeter, right?
Yes.
So if concretes are pulled apart by 6 millimeter, the fiber either pulled out of the concrete or they're just like really plastically elongated, because
yes, of course.
Yeah. So
as you can see here, for example, if we are on a crack with 5 to 6 millimeters opening, we are going to have less than 15-20% LTE, so actually no load transfer across the crack.
Yeah, so yeah, that's what I think is very hard. I don't know if fiber really made a big thing in this project. I don't know. Thank you.
I believe the Europeans actually use steel fibers in their roundabouts, so that might behave differently than the synthetic fibers that we're dealing with right now.
Yeah, maybe, yes.
I would think this ties into what Manik was talking in his presentation about the creep factor. As you stretch it, once it's stretched out, it doesn't come back.
Yep.
Yeah.
So for 6 millimeter crack width, fiber is really not going to stretch back.
Do much.
No. These are like kind of gone case.
Yes.
Any other questions for Hamad? All right. Well, I'd like to thank Manik and Sheue and Hamad for taking the time today to share some of the findings on the 3 projects. And Tom, you were recording this. Do you have an idea where it might be posted if somebody wanted to listen to it, or maybe have somebody else that was not able to participate? Is it going to be on the Rigid Teams site?
I will leave that up to Lauren.
Good answer.
Yeah.
All right. Anything? I don't know if Ben's still on. I don't know if there's anything else, but I'll, again, thank the presenters for the information. And on June 3rd, we'll have 3 more presentations. Actually, I'm assuming John's going to talk about the compacted concrete pavement.
Excuse me, Brett.
Yes.
I see a comment from Peter Taylor here. It would be worth comparing LTE and crack width from Manik's project with the data we got from FRC ring. I think it's going to add, more information. I agree with that.
Yeah, it's additional data on kind of. I think that's why Manik was so interested, because we're kind of seeing some stuff here that could help us. But it would be curious to see a roundabout with steel fiber, or steel fibers would be I think better suited if you're trying to get some sort of load transfer effect, or you're going to have to come up with a completely different synthetic material that is more, less susceptible to discrete. So, all right. Well, with that, unless Ben or Tom have any comments or anything like that, I think the next meeting again will be June 3rd. It'll be pretty much the same format as this, just 3 different topics.
You can also look for 2 one-hour webinars coming up that would have been the workshop and the day 3 of the conference. So those will be coming up. One will be by Peter Taylor, and then there'll be another one by Lev and Julie. And we're in the process of scheduling those sometime either later this month or during June. So those will be independent of these team meetings. Those will be 1-hour webinars.
Yeah, I think if you're wondering what that is, look on the agenda. And I think it was item 3. I think it's got to be scheduled. But again, those were topics that were going to be discussed. If I recall right, day 1 there was going to be a workshop. And of course, there is no travel, so we're going to have those as a 1-hour webinar each for people to participate. And I think one went out for soils geotech yesterday. I think a webinar invite. So start looking for that. They will start to show up, and hopefully you'll be able to participate. Well, with that, Tom, appreciate that information. And with that, we'll conclude the Rigid team meeting. Thanks for everybody joining. It looked like at one point we had 30 participants, so I appreciate the attendance and hope there was some beneficial information. And we'll let you know where the recordings will be posted, and we'll get back with you all on June 3rd. So have a great day.
Thank you.